Welcome everyone to today's special year seminar. Our speaker is Tongmu He, who is going to be talking about Sen operators in the algebras arising from Galois representations over p-adic fields.
Thank you very much. So it's over p-adic varieties.
Sorry.
Yeah, thank you for your introduction and the invitation. It's my pleasure to speak here. So we would like to construct Sen operators over p-adic varieties. So first of all, we consider the case of p-adic fields. So first we review Sand-Bruno's construction of Sen operators over local fields. So let me introduce some notation. So let K be a complete discrete valuation field extension of QP with imperfect residue field K. But I assume that the degree of K over KP is finite. In other words, I could take T1, Td, some units of OK, which are liftings of a P basis of the imperfect residue field K. So for example, such complete discrete valuation ring appear in our geometric case. So if I consider this smooth curve over ZP, so it looks like this, and we have generic point of the generic fiber and the generic point of the special fiber equate P, then the localization at the generic point of its special fiber is a discrete valuation ring with imperfect residue field. Okay. And we would like to study the representation of the absolute Galois group. I fix an algebraic closure of K, and I denote by G its absolute Galois group. Our main object of this talk is the category of finite dimensional continuous semi-k-bar hat linear representations W of G. So we would like to study the category of all the semi-linear continuous representation of this absolute Galois group G. So a priori, it looks complicated to study like that, but Sen and Bruno gave an approach to study such a category. So they consider a much simpler Galois extension of K. So let me introduce some notation. So we first consider the cyclotomic extension of K, which is given by adjoining all p power roots of the unity. And then I adjoin all the p power roots of the lifting of P's basis. And they are containing our chosen algebraic closure, K bar. And I denote some Galois groups like that. And we have G here. So we see that those Galois groups are much simpler in the sense that it contains an open subgroup isomorphic to ZP. This contains an open subgroup isomorphic to ZP to the D. So that gamma contains an open subgroup, the semi-direct product of ZP with ZPD. So we wonder that how many representations of G over K bar hat comes from the much simpler Galois group gamma. For example, if we consider finite dimensional Galois representation of gamma with coefficient in K infinity infinity completed, then the functor is the base change functor by extending scalars of this to that. How many representation comes from them? In fact, this is an equivalence of category because this is a perfectoid field. So So to this, we have almost the parity so that every representation here can be descended to a representation there. So this is an equivalence of category. Moreover, Say and Bruno proves that we can decomplete the coefficient of that. Namely, if we just consider the finite dimensional continuous representation of gamma with coefficient in k infinity infinity, then the base change factor is still an equivalence. And finally, I have to mention that we can descend further to representation of gamma with coefficient in k infinity, but I have to add a technical condition called by delta analytic. So this base change factor is still an equivalence proved by Tsuji. So this step I will use implicitly in my talk later. So this is a very technical part. So namely, the functor is given by sending v to here w is equal to the base change of that. And one can even write down the inverse of all these functors. So first, if I denote this by h, then I take the h invariant, I get the inverse of that. And then I take, how to decomplete it? I take the gamma k infinity, gamma k finite part, namely the submodule formed by those elements whose gamma orbit generates a finite space of finite dimensional space over k. And finally, I take the delta analytic part. I will explain what's the delta analytic mean. So namely, those equivalents are very concrete, and we can write down the inverses. So here, delta analytic means that for every element of delta and v is an element of v called delta analytic if the action of tau on v is given by the exponential of its infinitesimal action over v. Here, the infinitesimal action is given by the standard formula. It's the limit of a tends to 0 over a tau a x on v minus v. Okay. Okay, so now we have those equivalents of categories. We notice that the Lie algebra of gamma is much smaller. Is equal to the Lie algebra of the semi-direct product of ZP with ZPD. So namely, this is a QP space isomorphic to 1 plus D. So we can take its standard basis partial 0, partial 1 to partial D corresponding to each component. Notice that since V is a representation of gamma with decompleted coefficient, so now the Lie algebra of gamma acts infinitesimally on V. So we have those such things as endomorphisms on V. So I get those endomorphisms. So now, since every representation there comes from the base change of such V, so we can extend by scalars to obtain 1 plus D endomorphism of the representation of the absolute Galois group G. So these are called the sign operators. So this one is called the arithmetic sign operator, and the operator is called the geometric sign operators. So they have many properties to control the behavior of the representation W, such as those 1 plus D endomorphisms determine the isomorphism class of such representation, and also the generalized eigenspace decomposition associated to the arithmetic sign operator gives you the so-called generalized Hodge data decomposition of the representation.
Excuse me, so that's a linear K bar action or section?
Yes, linear K bar hat section, because those, because you see that here, the K infinity is decompleted. So every element of K infinity is fixed by an open subgroup of gamma. So this linear action is K infinity linear.
Oh.
And by base change is K bar hat linear. Okay, so, but today we would like to focus on the following proposition, namely those 1 plus D operators capture the inertial subgroup action on W. We have the following theorem, which is due to Sen for the perfect residue field case and generalized by Okubo to the imperfect residue field case. So consider a QP continuous representation of G. So we would like to study the Sen operator associated with that. So to define Sen operator, we need to expand its scalars to the big coefficient K bar hat. So we have as this change to K bar hat is our W. Notice that to define the Sen operator of W, we descended to the representation of gamma with the coefficient in K infinity. So we have this. So notice that these are totally two different directions. One keeps the complicated Galois group G, and the other reduces to much simpler Galois group gamma. So one would like to know how the Sen operator defined by this direction will control the behavior of the original p-adic Galois representation. So in fact, we have the following statement. So let I denote the inertial subgroup of G, and let rho be the structural morphism from G to the automorphism group of S. Then the Lie algebra of its image of the inertial subgroup here is a subspace of the endomorphism of S. It is the smallest one. Such that the Sen operators of W, the Sen operators of W are just some endomorphisms of W. So the statement says that it contains in the base change of this Lie algebra. Moreover, this is the smallest one having this property, namely this is the smallest one whose base change contains all the Sen operators. So there is a very special case to give you a sense of what this statement says. So namely, if all the Sen operators are 0, if and only if the inertial subgroup acts on S by through a finite quotient. Namely, the image of I here is a finite group. So that we say that the Sen operators essentially capture the action of inertial subgroup on our p-adic Galois group representation. Okay. Okay, so today our goal is that first we would like to construct Sen operators over p-adic varieties. And then we would like to generalize the relation with inertial subgroup. So the first,
Question,
yes,
what is Lie of rho I?
Lie of rho I. So rho I is a subgroup of automorphism of S. So this one is isomorphic to GLNQP, right? So it is so the image of rho I is a closed subgroup of that. So we can take its Lie algebra.
Okay, so implicitly it's like that it has an analytic structure.
Sorry.
So
It's automatic, yeah, every closed subgroup of a p-adic thing is also p-adic analytic.
Yeah.
Okay, thank you.
Okay. So how to construct a sign operator? Our strategy is in fact to glue the sign operator defined in the local field case. And by this construction, one can obtain a direct generalization of sign Okubo by this gluing process. Okay. But now the difficulty is that if the residue field is imperfect, not perfect, then those sign operators are non-canonical. They depend on the choice of your lifting of p basis. And of course, their p power rules. For example, and it seems impossible to find global sections whose localization at height 1 primes always give you the lifting of p basis. For example, if we consider the semi-stable curve of ZP, it looks like this. So we have component x equal to 0, y equal to 0, and we have generic points P1, P2. Notice that x itself, with respect to A, this is a good coordinate. In the sense that if I adjoint A with k infinity and the p power roots of x, I will get a perfectoid ring. Okay. However, such a good coordinate does not restrict to good coordinates of P1 and P2 by localization. This is a p basis for one localization, AP1, but not for the other. So this suggests that we should enlarge our consideration of system of coordinates. We should include such x as our system of coordinates and also their restrictions as our generalized system of coordinates. So the best we can hope is that we would like to find canonical Lie algebra action on each representation W, replacing the non-canonical one. Okay, such that once we fix the basis of that Lie algebra, then it will give back those non-canonical sign operators. So this is possible. So now we move to canonical construction of sign operators. We need,
I have a question.
yes,
So, what if your p-adic already have good reduction? I mean, in the kind of very good p-adic algebra, so that when you modulo p, you just have one general fiber. So in the
then if we change charts, then the same problem maybe arise. Yeah.
no way.
Yeah. So anyway, we would like to consider much more generalized system coordinates. So the canonical construction is possible because we can consider the Farking's extension of OK. So the Farking's extension of OK is a short exact sequence from K bar hat, I add a Tate twist to the Farking's extension I will define later with the quotient, the extended scalars of the differentials, the module of differential of OK over ZP, and I completed p-adic. So the Farking's extension is defined as the Tate module, namely the inverse limit of differentials of OK bar over OK. So a priori, this looks like very big, but the existence of Farking's extension says that this is actually finite free over K bar hat. It admits a K bar hat basis. Namely, we can consider the inverse system of d log ti 1 over pn. So this defines an element of this inverse limit from I from 0 to d. Here, my notation for 0 is the p power roots of unit primitive. So if we consider the dual of the Farking's extension and I give it a Tate twist, then I will get the dual of Farking's extension and then give it a Tate twist with quotient K bar. So this one has a canonical Lie algebra structure. Namely, it is given by two elements. The Lie bracket is, I apply this canonical linear form of that. And so you see that if I take the basis of that, take the dual basis of that, then we have a non-canonical isomorphism of dual of Farking's extension to Lie algebra of gamma. And if I denote it by T0 dual to to denote this, the dual of those bases, then we have those a simple form. Okay. So now I can state the canonical construction of cell operators of a local field. For any finite dimensional representation of absolute Galois group G with coefficient in K bar hat, there exists a homomorphism of Lie algebras from the dual of Farking's extension to the Lie algebra of endomorphism of W. Okay, which is G equivariant and functorial in W. How does it define it? We defined like as follows by the following concrete formula. So let S1, SE be finitely remaining elements of K. I only add the mild conditions on them. I assume that those differentials lies in OK hat invert P. I assume that they are K-linearly independent. And I call such finite remaining elements as our generalized system of coordinates. For example, in this case, the restriction of S to AP1 or AP2 satisfy this mild condition. Okay? And I can form a similar tower by these elements. So I have cyclotomic tower, and I add the roots of p-power roots of these elements. So I will get gamma prime, delta prime in our cable. Notice that in this case, we may not have a descent theorem of representation. So we need to assume that the representation comes from down. There exists a representation V prime of that whose phase change is W. So namely, for each W, there may be a lot of generalized system of coordinates. So we can form a lot of different towers. And each W, they may come from a different descent of representation. After all, there always exists such a descent of representation, because if you choose our lifting of P basis, then by the previous descent theorem of Sam, Bruno, and Tsuji, we know that there exists one. So we would like to compare those different descent of representation. So if we are given those data, then in this case, the Lie algebra of gamma prime, by the first condition, it is isomorphic to ZP semi-direct product with ZPE, and we can take its standard basis. Then the Sen operator is given by the following concrete formula. So for any element of the dual of Faltings extension, I can evaluate the element of the dual of Faltings extension to this element, Si, and I give it a Tate twist. So this will produce a scalar, and I tensor with the infinitesimal action of this standard basis acts on the descent of representation B prime. So in fact, this formula is only so if we consider the non-canonical isomorphism of Faltings extension with Lie algebra of gamma fixed after choosing the lifting of P basis on the left, then we know that this morphism defined by this formula sends the standard basis to the identity of this one, the previous non-canonical same defined by Sen and Bruno. So this is actually a generalization of their operators. Is the statement clear?
So this Lie algebra, does it canonically descend to anything smaller than a K-bar hat?
I don't think so. Yeah. Okay. So proof, we only need to prove that this non-canonical formula actually is independent of all of our choice. Is independent of the descent of representation, is independent of your choice of generalized system of coordinates. How do we prove that? In fact, we use the p-adic Simpson correspondence over OK, developed by Tsuji, to compute concretely if we change the generalized system coordinates, how this formula would change. In fact, it will not change, as our computation shows. So that we proved this theorem. Okay. So this proof is a concrete computation. So now to define the Sen operators over p-adic varieties, we have the following difficulties. So first, we need candidates of our canonical Lie algebra. So we know that it should be the Fartins extension, the dual of Fartins extension. And also we need a theorem of descent of representation. We have to see that such a descent exists for at least one tower. Okay. And finally, we shall use the similar non-canonical formula to define the Sen operator, and we have to prove that its value is independent of the choice of coordinates and the choice of your descent. So we will focus on the third point. Okay. So we move to the Sen operators over varieties. So let me introduce some notations. So now I denote K to be the concrete discrete valuation field extension of QP with perfect residue field. And let A0 to be a notary normal domain. Over OK with non-zero special fiber. And I assume that there exists a semi-stable chart of A0. A0, T1, PC, TC plus 1, TD, modular T0, T1 times TC, minus pi k is the uniformizer of K, and I add an exponent E. So I assume that there is an Adala ring map to A0. So we will see in the end why we need to consider such simple case. Okay? So now we consider the generic fiber of A0 and its fraction field L0. We consider a finite extension of its fraction field L0 such that its integral closure of A0 in L so this is the integral closure of A0 in L. I assume that this its generic fiber is finite Adala. Okay, and I denote by L unramified the union of all such finite extension L called the maximum unramified extension, and I denote its Galois group by G. So this is actually the fundamental group of this generic fiber of A invert P. And I denote the integral closure of A in maximum unramified extension by A bar. Okay. So now, in this case, we also have a Fartins extension. So it is a short exact sequence. A bar hat invert P, and I add a tight twist to Fartins extension I will define later to whose quotient is the extension scalars of the differentials. So here, the finite extension is defined again as Tate modules of the differential of A bar over A. Okay, it is in fact also if is equal to, if you consider the log differential, they are the same. Okay. So again, the existence of such Bartlett's extension says that this is actually finite free over A bar hat invert P. So it admits a basis given by d log Ti P and roots of that. Here, T0 is again the roots of unity, and the Ti is the image of the chart. Ti, okay. You see again that the Bartlett's extension unifies all possible system of coordinates, right? Because if you change this, it still lies in this module. So this will give us a good candidate of the canonical Lie algebra. Again, by the same formula above, this formula, we know that the dual of Bartlett's extension is still a canonical Lie algebra. Okay. So now we can state our main theorem. The construction of Sen operators over p-adic varieties. So for any finite projective continuous representation of the fundamental group G, arithmetic fundamental group G, with coefficient in A bar hat invert P, there exists a canonical homomorphism of the algebras from the dual of Bartlett's extension to the Lie algebra of endomorphism of W, which is G equivariant and functorial in W, and moreover, it is independent of the choice of the chart of the semi-stable chart on the right. Okay, so proof. So first we need to descend such representation to a representation with much simpler Galois group. So this is due to Tsuji when he developed the p-adic Simpson correspondence for semi-stable varieties. And I generalized his argument to fit in our case, because here we see that A is just a normal domain, and I assume that it is finite over A0, where A0 admits a semi-stable chart. We allow this flexibility to shrink this Galois group G, because we see everything is related to Lie algebra. So I would like to maintain the flexibility to shrink the Galois group G. So that's why we consider A instead of just A0. Okay, so we generalize the Tsuji's theorem for A0 to A. Again, to define the Sen operator, we will get the same formula as above, same non-canonical formula, a priori non-canonical formula. After choosing a chart or generalized. Although I didn't define in this talk, but I defined in paper. What does it mean? generalize the system coordinates in this case. It has the property that if I go to the localization of height 1 primes, then generalize the system coordinates will send to generalize the system coordinates over the local field. Okay, so finally, I will prove that it is independent of all the choice, such as the descent of representation and the choice of charts. How do we do this? We reduce to the local field case. Because over local field case, we have already established such theorem by localize at height 1 prime. Okay, so let me explain more details to the how to prove that independence. So consider the prime of a bar with height of 1 and lies on the special fiber, namely it is just a generic point of the special fiber, and consider its image, which is also a generic point of the special fiber of A. Okay, and I consider some localizations. I localize at P, and above I localize at Q. So this is a discrete evaluation ring, and this is a valuation ring extension of that. And I go to completion, go to p-adic completion. So this will be a complete discrete evaluation ring. And I consider its algebraic closure. Okay. So of course, there exists an embedding of that to that. So I choose 1. So here we have Galois group of this completed local field case, and here we have our arithmetic fundamental group. So the key ingredient of the proof to how to reduce to local field is the following injection. So if I consider a bar modulo p to the n, a bar to the product over all these height 1 primes q, and I consider those valuation rings modulo p to the n. This morphism is actually injective because a bar is a colimit of notary normal domain, and we have already controlled all the height 1 primes over that. So it will be injective. This is the classical lemma in commutative algebra. Okay. So now I have a finite projective thing representation over a bar hat invert p, so that it's, if I base change this W to this valuation ring, I get WQ, then it is injective by this injection. Okay. And on the other hand, we have our dual Fartings extension. There also has a canonical injection to the local field case, product of local field case. Okay, because it is finite free over that. We have already established a canonical SAN operator over the local field case. So there exists a Lie algebra action of that over that. Okay, and they are injective. So there exists at most one Lie algebra action of that over that, which is compatible with the local field case. Okay, there exists So, and on the other hand, so we have proved, because this injection implies that there exists at most one thing commutative with commutative diagram. So, but we defined this phi sen as using this same non-canonical formula. So, because this non-canonical formula is defined by generalized system coordinates, and the generalized system coordinates is compatible with localizing at height 1 primes. So by this formula, we know that this diagram is commutative. So the existence of such action is also proved. Okay, the uniqueness follows from the injection, and the existence follows from the same non-canonical formula. So we see that those action is the unique one, the unique canonical one, which gluing the action at height 1 primes. So this finished the theory.
Existence of such kind of thing, can you do the non-canonical thing?
Yeah,
and
yeah.
You check that you put into the.
Yes, they are commutative.
Have to be the canonical. So.
Yes, yeah. So this finished the proof of this theorem. So now I would like to talk about some applications like the relation with inertial subgroup. So by the same strategy, we can generalize Sen and Okubo's theorem directly to our case. So again, we have if we have a representation S of G with coefficient in QP, to define Sen operator, we need to extend its scalars to A bar hat invert P. Recall that the Sen operator is defined via some descent process. We didn't state before. Okay, so we have W here. And we would like to see how the Sen operator control the behavior of S. So that rho denotes the canonical morphism from G to S. Then, similarly, I need to do small notations. So for each P here, I have the inertial subgroup of the complete discrete evaluation field. And its image I denote by IQ, which I call the inertial of A bar over A at this height 1 prime Q. Then the sum of all of these height 1 prime Q of rho IQ, which is a subspace of anamorphism of S, it is the smallest one. Such that the image of the Sen morphism, namely the module of Sen operators, a priori, it is just a submodule of anamorphism of W. So the claim says that it contains in the base change, it is contained in the base change of the sum of the algebras. And moreover, the sum of those Lie algebras of inertial subgroups are the smallest one whose base change contains the image of Sen operators. So again, we see that the Sen operator is equal to 0 if and only if rho IQ is finite for every Q. Okay. On the other hand, there is another corollary, is that those Sen operators actually contained in the base change of the Lie algebra of rho G. So such corollary suggests us that the dual of Varieties extension behaves like Lie algebra of the profinite group G. So to make sense of this philosophy, we would like to mention another corollary. So let G have a curly G, a quotient, which is a p-adic analytic group. In other words, this is just a closed subgroup of some GL and QP. Then for any representation of this curly G with a coefficient in QP, and I consider its phase change, then starting from the dual of Varieties extension, there will exist a universal semimorphism for curly G to the extending scalars of the Lie algebra of curly G, such that on the left-hand side, we have a sem operator action on each W. On the right-hand side, we have an infinitesimal action for S. Okay, and by base change, this is an isomorphism. So the conclusion is that there exists a universal map from the dual of Varieties extension to the extended scalars of Lie algebra, such that for every QP representation of curly G, this diagram is commutative. So namely, yeah. So let's explain this philosophy. This dual of Varieties extension behaves like a Lie algebra of that. So finally, I would like to say some words about the globalization of sem operator, because we here until now we always consider the affine case, and we would like to globalize it. So now I consider X over S. I denote S by, so S is totally different from now. So S is the spectrum of OK. OK is the complete discrete evaluation ring over CP with perfect residue field. And the X is a scheme of finite presentation with smooth generic fiber. And we would like to construct the sem operators for the representation of a arithmetic fundamental group of X. Okay? So the first question is that how to reduce to the semi-stable affine cases, as we talked before. For example, if we consider A is equal to A0, how do we reduce to this case? So we need to consider a site called the generic ideal over X. So namely, this category is formed by Y over T over X over X over S. So now Y over X is again a finite presentation of schemes. And T is a spectrum of OL and Y over X is a finite presentation such that the generic fiber is a DAL. and L over K is finite. Okay, so the category formed by these morphisms. And the topology is formed by the V topology or V topology on Y. So in other words, we can prove that this topology also generated by the admissible blowups. And also the faithfully flat coverings. Okay, this is the generically idealized of X. So this was considered by Varieties long ago and also by Temkin. And the theorem of Temkin says that locally over this site, we can get those semi-stable. So if we consider the subset of those semi-stable affines, then it forms a topological generating family. So namely, this is a topological basis. So that's why we consider those semi-stable charts with such an exponent E. So Temkin only proved that case. So that form of semi-stable will form a topological basis of this generically ideal site. Okay? Okay, so the other question is that how to interpret the representation, continuous representation of G with the coefficient in A bar hat invert B. So this is again. So in the case that Y is equal to the spectrum of A, then we can consider the pro-finite idealized of its generic fiber. Namely, objects are schemes pro-finitely ideal over this generic fiber YK. And we consider a structural shift defined as follows. So we consider the integral closure of Y in V, and we consider this B bar, which is defined over that, defined as follows. Okay, maybe I should add some. And shiftification, we will get B bar as a structural shift. Over IK pro finite double. Okay, and why we consider pro finite side? Because it will interpret those representations. So namely, if we consider all the vector bundles over YK pro finite with the coefficient in B bar, I give it a p-adic completion and invert P. Then this vector bundle is canonically equivalent to the category of the continuous representation of G with the coefficient P. Okay. So now we have all the ingredients to globalize all we have said in previously. So now we can consider a fiber category called Varieties site. This is a fiber category. Over this generically idealized. Namely, for every object Y over T, I consider is profinite ideal site of its generic fiber. So we can state our construction, globalize the construction for every W, which is a vector bundle over this Varieties site with the coefficient in B bar has invert P. Then there exists a canonical homomorphism of Lie algebras. from the Schiff version of Falken's extension, dual Falken's extension to the Schiff of endomorphisms of W. So I will stop here. Thank you very much.
Questions?
I'm sure you want to say something about the property of this.
The property of this, in fact, I'm still studying it. I mean, all of the interesting properties can be seen locally. Yeah, and it is hard to state all the property in the global form. So, yeah.
Okay, how is this related to this canonical Higgs field that we on V bundles?
So we see that there is a submodule like that, the dual of differentials. So the dual of differentials is a submodule of that, and this part is called the geometric semimorphism. Geometric semimorphism. So the geometric semimorphism can be also written as something like a W to W tensor with the differential, right? And this is the Higgs field associated to this vector bundle. I mean, geometrically, yeah.
Yes, I'll try to understand the Shen operator for the geometry Shen operator. More explicitly, so suppose I have the like a crystalline representation, then you have something decrease or something, and we know the classical Shen operator give you halted weight. And is there anything about the geometry Shen operator give me something? For example, that we have a connection or the decrease, is that somehow connected with your geometry Shen operator?
So again, the Hochschild weight should be given by the arithmetic Shen operator. So in the local case, we have this thing mapped to phi Sen to the endomorphism of W. Okay. And in this case, yeah, for example, in this case, so you know that you see that there is a lot of lift of the one here, right? There are a lot of lifts, but no matter which lift you take, let's say F is a lift of one here, then phi Sen F is an element, is an endomorphism of W. This is called an arithmetic Sen operator, and its eigenvalues are the Hochschild weights.
Yeah, like
Are exactly the Hochschild weights. Yeah.
I mean, for the geometry, if you have parameters like P, so that thing tell you anything particular for the representation. So.
I haven't studied it. So.
Oh, okay.
Anything further? Yes, yeah.
Is it present this construction in some sense is independent of the formal model? Sorry, of the integral model?
I mean, if we use the scheme theoretic language, we always take an integral model, right? Because here I start from X over S, which is a finite presentation with generically smooth thing. So I start from such an integral model, although I didn't assume any nice property of this special fiber. But I think if we would like to do p-adic completion in the scheme theoretical case, we have to fix an integral model at first.
Okay. So, and does it generalize to Regis basis or?
I think so. I hope so. Yeah. Yeah, but yeah.
Sorry.
For example, if you consider In fact, this generically idealized is a scheme theoretic analog of rigid spaces. If you consider, you can define some structure shift O over that, which is the restriction of p bar hat invert P over that. I call it O. Then the coherent modules over that is equivalent to the coherent modules over the associated rigid space. Okay. Yeah. So yeah, it's just stated in scheme theoretic languages.
Great, thank you.
So just to make sure, so this X over S generic tau, is the topos not the same as the tau topos of?
No, it is not, because we allow the miscible blow-ups. Okay, right? So it is not the ideal topos. You mean the ideal topos of the rigid analytic generic fiber?
Yeah, something like that.
I don't know. I only know how to compare the coherent modules of them, but I don't know.
But also, if you just do a divisible blow up, wouldn't the general fiber also be tau?
Yeah, I mean, but everything are schemes, so yeah. We know that there is a map from this one to this one. There is a map, but I don't know if they are the associated topos are equivalent or not.
I don't know, like, I think they allowed finite flat covers there. Maybe it's.
Basically flat covers. Yeah.
Yeah, so it's finite.
But
There might be basically flat, but not generically.
But his objects are always.
Okay.
yeah.
I don't understand why B bar hat 1/P lives on G on X sub S, XS.
I mean, the restriction of that, I should say the restriction of
The push.
this is, yeah, push forward. Yes, the push forward. Sorry. I should. Or maybe it's.
So it's much smaller, okay.
Yeah, much smaller. Yeah.
If there's nothing further, let's thank Tongmu again for his talk.